unmute myself. My name is Kipfer, and I'm with Neoti, and here to talk to you today about LED displays, direct view LED displays specifically. So if you were hoping for TV displays, you're in the wrong room. But direct view LED displays are what we're here to talk about today, and then specifically what about them on camera. So before we get started a little bit, I want to know from you guys, how many of you deal with direct view LEDs on a daily basis, or at least with your customers or anything? Anybody? I got one. One hand. What are you doing up here? Like, what's the purpose? Okay, so how many of you are here? Have you ever dealt with direct view LED, specifically on camera? Okay, all right. And, or at least talk to somebody that has, and talked about the headaches of what it is. Okay, I wanted to get a sense of kind of who I was talking to here before we get too deep in the weeds here. I kind of have a broad overview. There's a lot of information that I'm not covering today that requires a whole other seminar once we start getting really deep into the technical aspects of everything. But for the most part, we'll get through everything that is the common issues that are faced when you're dealing with direct view LED. So who is Neoti and why are you listening to me? We began in 2006 as a digital signage company, morphed into a direct view LED company in about 2008, 2009, and specifically targeted the broadcast market. So for the first 7, 8 years of Neoti's infancy, we were only broadcast related direct view LED. We weren't in the corporate spaces, we weren't in educational spaces, sports stadiums, things like that. And so for us, our focus was always on the narrow pixel pitch or the really high resolution product and on-camera performance for high critical environments, because we knew if we were able to create a name for ourselves in that space, then we could push out into the corporate spaces with no problem, push out into like the critical environments like for DoD or things like that with no issues, because we were already used to high demands and high output type of product. And so that's what we have done. That's kind of our pedigree from now until till the future. We're still very highly focused on-camera performance, color performance, and some of the things we'll talk about a little bit later. But we've been doing this, again, for about 17 years now. I've been with Neoti for 16 of those years, so I've seen a lot of changes that have happened along the way. Back when we were starting with 20 millimeter product, now we're talking about 0.6 millimeter product. So a lot of different changes and a lot of, especially for on-camera performance, changes as well. So when we talk about cameras and direct view LED, we talk about a relationship that is a great relationship because it affords opportunities that we couldn't do with like green screen and things like that, other environmental aspects of having LED in the actual environment so that people that are interacting with it can see what they're doing in contrast to what a green screen provides. But with that comes a lot of new challenges. Some of them you see here on this slide, things like scanning issues over here on the left. You see moire kind of happening here on the Olympic rings, and then more different types of scan lines happening below. And so we're going to talk about a lot of those different things. These are the most common issues that are dealt with when you're pointing a camera at a direct view LED screen, and I'll talk about why. So the first thing we're talking about is moire. This is the most common question, and this is the one that everybody knows about. They may or may not know how to deal with it, but they know that it exists. And that's when you point a camera at an LED screen, whether it's your iPhone camera or whether it's a broadcast camera, and you start to get the wavy lines or the interesting designs that you start to see that you don't see with your naked eye. Why that is the same way if you had two pieces of screen, like for your door or your window, and place them over top of each other. All that's happening is that those patterns are overlapping and creating a new pattern. By themselves, they each have their own pattern. You put them together, and there you go. Now you've got weird wavy lines. Why is that important for camera? Because the LED themselves, if you look at an LED, I brought one here, but it's a high resolution one, so it's kind of hard to see. But if you look with LED in general, you have a grid pattern of some sort because of the way that the LEDs are placed on a board. And this could be the same type of grid pattern that's on a stadium screen, that's a much lower resolution product, or on something like this that's really high resolution and there's so many of them, they're still a grid pattern because they're placed on there that way. In your cameras and the sensors, those sensors also have a grid pattern because they're built generally the same way, with being able to introduce light to them. And so when the camera has a grid pattern and this has a grid pattern and the camera can pick up on this grid pattern, all it's going to do is overlap the two as it's viewing it, which your eyes don't do. Your eyes tend to understand that sort of thing because your eyes work in a completely different way. There's no grid pattern to the internal components of your eye. But on a camera, that's why you have the issue, is because you're picking up on that grid. So how do you get rid of it? There's lots of different reasons, or lots of different ways. The first thing is to plan ahead before you even install an LED screen. And if you're an operator, especially a camera operator, you may not be in that discussion. You know, it may be procurement or it may be somebody else in IT that's making the decision. But you can at least influence the decision and speak up, because if you put in the wrong LED, even if it's something like this, this here can still show moire, even though it's such a high resolution, because it relates to the application of the environment and how far the camera is away. So the first thing to do is always decide what's the correct pixel pitch, which pixel pitch is just the distance from one LED to another. What's the correct pixel pitch for your room or your environment, that your studio space that you have your cameras in? Because all you're really trying to do is keep the camera from focusing on the LED. Because when the camera focuses on the LED and picks up on that pattern, you're going to have moire, whether it's a high resolution product like this or a 16 millimeter product. It doesn't matter. As long as it can't pick up on that pixel pitch, then you're going to be okay. So if you're in a really small room, you need a really tight pixel pitch like this. You need something that's really high resolution that the camera won't be able to pick up on. And more importantly, in studio environments, you usually have talent or a desk or something in front of the LED, and you're using the LED as a backdrop. You have to determine how far away is your focus point, not necessarily just from the camera to the screen, but where is the camera focusing? So if the camera is focusing here, then you need to make sure that there's enough distance from here to there that the camera won't be able to focus on your point of focus and still pick up on the LED, because that can happen as well if the screen is too close to the person. So that's why sometimes when you're watching broadcasts, whether they're live broadcasts for like sporting events and they're standing in front of an LED screen or something, you can see, you know, moire behind somebody if they're standing in front of an LED backdrop. Or even some shots in broadcast environments where they've spent money to try to alleviate it. There are still some angles and things that will still catch the LED in a way that allows it to pick up on that moire pattern. So you have to be careful, first of all, what pixel pitch you use, because if you use the wrong one, it doesn't matter. Unless you can get your camera 50 feet, 60 feet back, or get the person in front of it, 15, 20 feet away from the LED, then you're going to be in trouble. It doesn't mean that you can't use lower resolution product in camera environments. It just means that there has to be enough distance that it can't make out that pattern. We had what studio was it? There's a studio here in DC, the Meet the Press studio here in DC, that they put in a 2.9 millimeter product in a broadcast environment. They had like 4 walls that they put a 2.9 millimeter product, which are spaced little more than double the width of these. So very low resolution up close. You can see the pixels really clearly. But their center focal point was a desk in the middle of the space that was much larger than it needed to be. And so there was about 20 feet from the person at the desk to the LED, and it never picked up. I say never, there were times that it did, but for the majority of the time, it never picked up on that pattern, just because the camera could never focus on it close enough. So that's step one. We talked about this a little bit, just change the focus. There are lots of different things you can do. You can play with the depth of field. You can use different lenses to try to reduce the amount of focus that it has on the LED, because, again, the focus is what's key. And then there's also other options for filtering things out. So you can shoot with anamorphic lenses. You can use optical low-pass filters in your lenses. Some of them come built in. Some of the cameras, have them nowadays because so many people are using LED. Those options are great, but it's still going to soften your image more so than anything else. And so not only is it going to soften the fact that it won't be able to see the pattern, but it's also going to soften the people in front of that as well. And so it's kind of a trade-off. If you don't mind a little bit of a softer image, then go that route. One way that you can also, I don't know if it's on this slide. Yeah. So another way that you can do it is if you want to save money in a studio and you're just looking for a backdrop that can be a little bit blurry, say maybe you want the effect of it being behind like frosted glass or something like that, and you just want to be able to throw movement behind it that you can't do with just a light box. There are customers that will put rear projection film in front of LED. And so you can use a really, really low resolution LED. We've had some studios use 10 millimeter LED, which is basically the same thing as they put in stadiums. So up close, it looks like a light bright, but behind a rear projection film, you back it off about an inch, inch and a half, it really blurs the image enough so that the image is really blurry, so they only use it for certain applications, but it allows them to control it more, give it more options than just using a standard light box. So that's enough about Moray. Pattern is the key, making sure you're not focused on it. The other thing that is a bigger issue, especially now with the changes in some of the cameras. So you have global shutter cameras, you have rolling shutter cameras. We've got a lot of different options now for camera systems. And all of them pick up LED in different ways because of the scan rate of LED. So scan lines are what you see here. They can be just rolling lines like you see in the Mary Poppins clip there, or they can be jagged edge lines that can be moving across the screen. We'll talk about why that is. But scan lines are probably the bigger headache outside of Moray because sometimes there really is nothing you can do about these if you choose the wrong LED. So before we understand exactly what it is, we need to talk about a few different things. So with LED, there are a couple terms that are used kind of interchangeably. Some people know what they are, some people don't. But the first one is refresh rate. So that's the amount of times that the screen itself can turn on and off, because with LED, there's no dimming of these. They're either on or off. So what happens is that they're refreshing, they're on and off at such a rate that your eye can't pick up what it is. But as you dim LED, it just changes the amount of times that those are on and off. It's not actually really dimming it like we would consider dimming a light. So that is what refresh rate. Scan rate is the number of times, the number of scans, basically, that the LEDs are on and off. So the way that LED is created is that a module this size has a lot of different smaller sections that are being controlled by one of these or three of these chips. Three, or actually about four of these chips. And so a small section of these chips is, or a small section of this board here is being controlled by a small section of these chips. Because of that, it's not an always-on type of a situation, just because in order to do that, you can only control so many lines at a time with these chips without overloading the back of this board to the point that there's not enough space for these chips to actually control here. So what happens is that there's scan rates that are part of specs when you're looking at LED, and it's only lighting up. So if, say, for instance, one group of ICs, one group of these chips are controlling a section here, it's not this whole section on and off. It's actually a fourth of this section or an eighth of this section or a 16th of this section every pulse. And so it's really just scanning down that section, but just very fast based on the refresh rate. So it can't pulse faster than the refresh rate, and it can't light up more of those sections than you have chips for. So that makes sense. So if you basically get this type of if you were to really slow it down, this is what it looks like when you're looking at an LED screen, is that you're only lighting up so many of them at once. So all the red ones are lit up and all the black ones are not in this situation. But it's doing this at such a rapid space, and it's scanning down that section so that you just don't perceive it with your naked eye. And so this is an example of a 1/16 scan. And this is an example of a 1/8 scan. So what's happening is that the higher this scan rate, so if you're talking about some LEDs 130, 140, 160 scan, it just means that very few are lit up at one time. And if you have a fast enough refresh rate, that's going to be okay, because it's basically a balance of the refresh rate and the scan rate determines whether or not your camera will actually pick that up. Because what happens is if your camera isn't, if it's refreshing slower refreshing faster than what this is scanning, it's going to pick up on those black sections that are in between scans. And that's why you get the rolling lines, the black lines. That's why you get some of the jagged lines that you see, is because it's actually picking up what your eye can't. It's picking up those black areas of the in-between sections. And so you have to make sure that the scan rate that you're purchasing is quality enough for the application. And one way to do that is to calculate the multiplexing rate, which is basically the refresh rate divided by the scan rate. So you take, if it's say your LED screen is a 1920 refresh or a 3840 refresh rate. You take that, you divide it by the scan rate. That scan rate is typically provided to you by the manufacturer. If it's not, you can ask for it. And then you divide that by your frames for your camera, and that gives you a number. That's the multiplexing rate. So in this calculation, the LED screen was 1920 hertz at 1/16 scan, and you're shooting in 24 frames per second. Do all the dividing, and you get to your multiplexing rate of 5. Well, if your camera's at 24 and your LED screen's at 5, that means there's a lot of frames that are going to be black that your camera's going to pick up on between 5 and 24. So the ideal rate for multiplexing is to be a higher rate than your camera, than you're shooting in. So ultimately, if we change the 1920 to 3840, then we'd be, maybe closer to 10, or even higher than that. So you just want to make sure that your multiplexing rate is higher than your rate of shooting. So that's the biggest consideration. Another consideration that is generally first looked at is gen locking. So especially in broadcast environments, you want to make sure that all your sources are locked in general. It just solves a lot of little problems. Scanning is sometimes one of them. Sometimes it has nothing to do with the multiplexing rate or anything. There just could be noise in the signal, or the timing is just a little bit off between what your LED screen's doing and what your camera is doing, or all the way through the chain. So making sure that you have a gen lock signal, some sort of reference signal, whether it's black burst or anything else, you just want to make sure that you have that in line. And especially for rolling lines, things like that, it'll take care of that for you. Another big issue that's becoming a bigger issue is color shift. So it's a little bit difficult to see in this example, but you can see that between this color and this color here is a little bit more red on the side. It's because LED screens, in general, like any display, have a viewing angle limitation. So if you take this, it looks white, take it like this, what you guys are going to see is more of a red color because of the way that the LEDs are shaped. You're seeing more of the red color from here because that's the brighter color of the three, of the red, green, and blue. And so that is especially more popular when we're talking about things like this, studio desks, right angle corners, curved displays, things like that are becoming more popular in studio design. All of those are introducing new things for the camera operators to deal with, and color shift is one of them. There are much worse examples than this one. In the worst case examples, that right side would be much more red or much more green than anything else. So just knowing that exists is the biggest thing, because there's not a lot that you can do about it once it's installed, outside of adding some third-party color correction to the mix, which some studios do. they'll correct just one side of it. So to the naked eye, that one side may look really blue or really green, but to the camera, they both look the same. And so that's the one way around it. But then that adds more equipment, more points of failure, that sort of thing. So sometimes you can just alleviate it by knowing where your camera angles are, by planning ahead and thinking through all of your shot blocking and everything to know where am I going to be shooting from, what considerations do I need to do. And then we always recommend, in studio environments specifically, test it out. Ask for a couple panels from your supplier and put them on camera, put them at the angles that you want to put them at, and see what your limitations are. And then how can you fix it? Like I said, it's really just about the angles. Change your shot blocking, change where you're doing things. We have one studio that had a really big problem with it because they decided to go from a colorful graphics package to almost all white, which, if any of you know LED, white is the worst color for LED because you're technically seeing red, green, and blue. You're not seeing white. And so shifting can happen tremendously on white when you're talking about a lot of weird angles. So what we would typically recommend in those environments is to stay away from white, stay away from light colors. If you already know you have so many angles that you're working with that it's going to be a headache, stick with colors that are going to hide it more, because there are times when there's nothing you can do about it. You're going to have that angle, and it's just part of your design, and the designer is just adamant that you have that specific angle. And if you can't put a color corrector on it or anything like that, use colorful graphics. Use things that aren't going to show up as well. Sometimes white is the worst. Red can also show some pretty decent color shift. Blue and green are a little bit more forgiving in color shifting, just because of the properties of the light. But having multiple colors in a shot or in a design like this one can hide a lot of that. And then really lastly, for what I have today, some of the things that are not talked about a lot yet, but are starting to become a little bit more popular, certainly one that we're taking more note of, is color accuracy, grayscale performance, some of the higher end side of LED, because LED inherently just produces the color that it produces. And I was having a conversation earlier about this, where it's very subjective in most studio environments, or most environments in general, I should say, is where they turn it on and it looks generally how they want it to look, and they're like, yeah, it looks great. Not necessarily taking into account that maybe skin tones are much more red, or skin tones are much more blue, or your whites are a little bit more red than they should be, or your colors just don't match what the real world environment is. It's kind of like going into Best Buy and seeing an oversaturated TV screen and getting it home, and then it doesn't look anything like that. People are so used to seeing bright, vibrant colors that there's been this shift away from what's natural. And so one of the things that we're talking about more is color accuracy, being able to really dial in true colors. So if you're working with Coca-Cola, for instance, they have a very specific red color that they mandate with pretty much anything that they do. Well, if you're buying an LED screen for Coca-Cola's lobby, for instance, most LED screens will produce red, but you're not necessarily going to get that one particular red. They may have to dial it in to get close, but there's usually limitations on the control systems and how it works. However, if you could match it to a color profile that they have, that their graphics people are using, and then produce that same color profile on an LED screen, now you're working with a completely different set of tools that allow you to do that. And so talking about, the way that you do this, the way that you control this is by the control system itself that usually the LED manufacturer is working with or building themselves, and then also the components that are used in your LED screen. So this same module that I'm holding could be made with the same layout and the same general function, could be made probably about 20 different ways. And from way 1 to way 20 would probably fluctuate in price by about 40%. And so there are so many different ways to make. There's so many different chip manufacturers. There's so many diode manufacturers. So many PCB manufacturers that are actually making the boards themselves. And so when it all gets finally put together, that's what matters. And making sure that the product that is being ordered or the product that you're using is working right for your application, because an off-the-shelf LED screen doesn't work for every single application. And if you're not paying attention to the components, you could be overpaying for LED, or you could be underpaying for the results that you actually want to get. And most LED manufacturers don't really care as long as you're paying. And so make sure that, the last thing I'll say is make sure that if you're buying LED, or if you're working with LED, if you know somebody who's buying LED, make sure you know exactly what you're getting. Don't look at just the price, because like I said, the price can fluctuate from one quote to another by easily 20%. And most people will think, well, I can get the same LED from this company for 20%, but there's a reason for that. LED manufacturers aren't stupid. They know what they're doing, and they're generally not telling you all of the specs, all the specifications that you would need to know if you knew what you were looking for. And that's why price fluctuates so much. So that's a freebie. Take that for what it is. But it affects everything that we've talked about today. If you buy the wrong LED, some of these problems can't be solved, even with the techniques that I've talked about. Because there are situations where on camera specifically, if you buy something with too high of a scan rate, or if you buy something that's not the right pixel pitch for your space, you're just gonna have a headache forever trying to fix it, or just living with it. So it's always best to know what you're getting ahead of time to alleviate many of the issues that LED brings. We've got a few minutes here. Does anybody have any questions? It could be about this, it could be about LED in general, I don't really care.
Going back to the Genlock.
Yeah.
Where in the LED portion do you generally Genlock? Is it the thing that generates the graphic at the beginning, or is there Genlock somewhere further down the path?
No, so LED architecture in general is that you've got your source and anything you have going on upstream that's coming to our control system, the LED controller, and then that LED controller is just sending a signal to the LED screen itself. The Genlocking happens in that control system, and then it passes it through to the LED.
So if you're doing this kind of situation, like in the studio, you want to make sure the control system has a Genlock input.
Correct, yeah.
Presumably they sell ones that don't.
Yeah, there are some that don't, yeah. So there's standard ones don't have it. Anything that you would want to put in a studio, we always recommend, even if you don't necessarily need it, because there are some studios that get lucky and everything just turns on and works. Most studios don't. And so we always recommend that there's at least the option for it. That way, even if you have to go out and buy a, Ajo device or a Blackmagic device or something and throw it in there, you've at least got your option to do that. Any other questions? Yeah. The pixel pitch is the first factor of how much an LED screen costs. The chips on the back is the second factor, because these are what actually drive the LEDs on the front. The LEDs on the front are nothing more than just the same type of LEDs you see in lights and things. They're just an RGB chip inside of a package. These are what actually drive the circuits. So this is definitely the more costly part, but followed closely by this, because these can range from, like I said, these can fluctuate 20 to 30% just in this area here. There are different ways to make these. So the majority of them now are, for indoor applications, are copper-based. So within each one of these little pixels here, there's an RGB chip, and then those chips are connected to the bottom of the chip that it connects to the board by either gold or copper filaments, basically. And if you buy copper filaments. Just the downside is that your failure rate over time is going to increase. Not by a ton, but it's going to increase. And when I say failure rate, I'm talking about individual pixels going out. So not like the whole thing stop work. The whole thing will still work. You'll just have a lot more failures in the pixels themselves. Especially if you're in a humid environment or you're in a dusty environment, copper just breaks down much faster, corrodes faster, everything else. So, but the difference between copper and gold is about 30%. So, like I said, just that one change can change the price of your screen 30%. When we first started producing product, we did everything in gold, just because we saw the value in it. But as you know, everybody started driving the price of LED down to nothing. Again, it all comes from somewhere. So everybody should know that the fact that LED prices are coming down aren't because manufacturing prices and costs are going down. It's because everybody's just using worse components than they were 5 years ago. Because it's the same thing. But yeah, so so now we offer kind of both options to customers. So, but that's just like, again, one example of what it takes to produce these.
Can you say anything about some products that are adding other color LEDs, as I understand it?
Yeah, they're going to come with their own set of challenges. Yeah, I mean, there's not a lot to say about them because not many people are doing them. There are also some manufacturers of controllers, like Brompton and some others, that are adding additional levels of adjustment to even RGB, to where you can adjust like the yellows and things like that. But a lot of that it's all image manipulation. It's not necessarily LED manipulation, because LED is still mostly RGB. So there are some that are doing RGBR. They're adding a red to basically create what's called a virtual pixel pitch. It's like pixel sharing. And so within the same package, I could call this 1.2 millimeter a 0.7 millimeter as far as how it's driving the actual pixels, but it's still 1.2 physical millimeters. But some manufacturers will add another red chip into there, and all the ones around it will share it. Yeah. The effect isn't great, and it's really more of a sales tactic to say, I could give you a 0.7 instead of a 1.2 for the same price, but really it's not. And when you're looking at it, it looks the same to me as a 1. You can tell between a 1.2 actual and a 0.7 virtual, they look nearly identical. And it also, anytime you add more colors and the processing hasn't caught up with it, you're going to start seeing more artifacting around the edges, especially between white and blacks. So like text and things like that, you'll start to see more weird colors happen because everything is geared towards just the 3 RGBs. So as we start to see new technologies come out, those are going to be the challenges, is making sure that it all works together correctly. Yeah. Yes?
I came a little late. Sorry.
Yeah.
How about the binning or the diodes?
Hi, my name is Aaron Kipfer. I'm with Neoti. The binning? Yes.
Well, I was just thinking and looking at that, and it's quite consistent, but what's your thoughts?
So that is also another way to cut costs. I'm telling you, there are a million ways to cut costs on these things. And it's the Wild West, so every manufacturer does what they want to do. And that's why you have to be really careful with the manufacturers that you choose. Now, generally, the large manufacturers, or ones that have been in business for a very long time, know that, and they're going to be a little bit more forthright, but not always. So yeah, for those of you who don't know, the individual LEDs that on the front here are produced by LED manufacturers. The manufacturing and LED are a lot of vendors coming together to create one product. So when somebody says I'm an LED manufacturer, that can mean a lot of different things. It could mean they're white labeling somebody else's product. It can mean that they're actually engineering product themselves and just having a factory make it. It could mean that they're a factory and engineering the product and doing it all. But even they may not be doing every single component. So it's very much a conglomeration, kind of like an Apple product. You may have one person designing it, but then there's lots of people that are actually making it. And so when you're making LED, or when you're buying LEDs, the millions of these things that you buy for one project, those are coming from a diode manufacturer. When they're produced by the billions and more at a time, and each one of these individual little chips here is tested for its light properties, for its light emitting properties. And so, and it goes through a machine, very fast, and it gets sorted based on its properties, plus or minus, the different levels that they have. And so they want all the light kind ones to be together because that's what's going to produce a more consistent looking finish. Because like he was saying, when you look at this, generally, even at black, it looks fairly consistent. If you have a product that was made with either mismatched or multi-bin matching, where they basically take a bunch of bins, put them together just to make a product quickly, even at black, you'll notice because some of it'll look more pixely, even when it's black. So you'll be able to make out that some of them will be blacker, some of them will be a little bit lighter colored, things like that, which not only affects it at black, but more importantly, it affects it at color, because now you've got this kind of pixelated. You can't really put your finger on it, but it looks a little bit pixelated. If any of you have ever seen bad looking LED, generally that's why, is that the LED themselves are bad. Now, nobody makes perfect batched LED. It's just impossible to do. So even the best ones at the time of manufacturing are only within 1 or 2 percentage points of each other. And then part of the final process of manufacturing is the calibration process. And that's where a camera is actually focused on each one of these, or a panel, or an entire screen, depending on how it's calibrated. And then the camera takes into account the entire pixelization of this module or of this cabinet, and will smooth everything out, basically. It'll adjust individual pixels. And every receiving card or every control manufacturer has their own way of doing that. Brompton has its own proprietary camera system that does that. Novastar uses, they have a camera, but they can use like Canon cameras and things like that to do that. It can be done in the field in most cases as well. So if you've got a screen that's been running for a long time and it's lost some of its calibration, you can actually go in and recalibrate it. Things we didn't talk about were like burn-in. That's technically a thing with LED. If you've got a company that uses it in a lobby environment and they run a logo on it 24/7, over time, you switch it to something else, you're going to see that logo burned into it. Not because it's technically burnt in, but because you've degraded those LEDs that were lit up for so long. But that can be fixed with LED. You can point a camera at it, recalibrate the whole thing, and it'll smooth everything out. Basically, what it'll do is it'll take all the really bright ones and dumb them down to the brightness of the ones that aren't. So yeah, that's the great thing about LED, is it is so versatile, and the longevity of LED outshines anything else. These things run at 24/7. You can easily expect them to run 10 years operation, because most of the time they're running at about 50 to 60% brightness. That's not unheard of at all to run that long or longer. So your long-term return on your investment for this, even if it's more upfront, is much better. And then if there's ever any issue, you pull one of these out of an entire wall, replace it with a spare, and you're back in business. If you've got a TV monitor wall or a projector or something, and something happens, you're out an entire TV or out an entire projector. So yeah, and then these can still be repaired. Something happens to this, as long as it's not like major damage, these can be repaired, and you'll never run out of spares. You'll just keep cycling through repaired ones. So I think we have time for, maybe 1 or 2 more.
What about power and heat? I had the impression that a big LED wall was going to be more power hungry and generate more heat than an equivalent of other LCDs.
Yeah, generally, yes. It is both of those things. It's more powerful and more hot. You do have to take that into account with the BTUs per hour, making sure that your system will be able to keep up with it. Because even at black, it's still producing heat, even if the screen's black, because the power supplies are still emitting some sort of heat. Now, there are options for like off-board power, where you can put power supply in a rack room, all the power supplies in a rack room, and run low voltage cable just to the LED. There are options to mitigate some of the heat properties that way. But power-wise, they do draw quite a bit of power. Now, there's max power, there's average power. Max power is typically the spec. Most LED providers will provide a spec for both. Max power is usually pretty hot. Because that is calculated by turning it on white and running it at 100%. It means you can run it without tripping anything as long as you have that many circuits. Average power is generally about 40% of what max power is. So you're not running it as hot as the specs say you are, but it still runs, it draws pretty decent amount of power. With this, so there's multiple different types, which we didn't talk about, but there are multiple different types of LED. This is an SMD product, meaning it's surface mounted to the board. That's prepackaged into little diodes and then surface mounted to the board. There's COB product that's out there now, and have been for a little while, where the red, green, and blue chips are mounted directly to the board, not through separate packages like this. And then there's flip chip COB, which is a whole different story. But with flip chip is where we're starting to see some of the micro LED and things going. The energy consumption and the heat are being reduced by about 30% with that technology. So it's a little more expensive right now. It's not typically what's going out the door. But we are seeing some technologies that are giving us lower rates of consumption all around the board. So that's good for everybody. But it's still a little bit of ways off before it becomes super popular, maybe a year or two off before we start seeing it all over the place, because it comes with its own other challenges. Any other questions? All right. Well, thank you guys for coming. I appreciate it. I hope you learned something.